Yeah, I mean, I can certainly start from the perspective of the design engineer or the analyst, right? So again, what we're doing is we're connecting in a very sort of parametric and live way our mission profile, our situation, orientation, relative distance, a line of sight to things like the sun, right? And so as a sort of a structures thermal guy, the first application I think of how this is important to integrate is I want to know, for example, the total thermal load that the worst case, for example, a particular electro-optical assembly might see, right? Because optics, for example, are hypersensitive to their temperature and their temperature profile. So we might say, hey, this EO assembly has to be on a structure, and the structure's mission profile looks like this. And so what we would usually have to do is say, okay, what's the worst case? And it's not easy to pick the worst case. It's hard to kind of just look at a piece of paper and say, okay, well, here's time, here's relation to the sun, here's a solar load, here's the power, dissipation of the electronics, and trying to combine that together. And so a lot of times what we end up doing is we end up just getting worst case scenario of everything, piling that on as a thermal requirement and designing to that. And so sort of the downfall of that, you end up over designing, right? And there's one
Hmm.
thing that we really don't have a lot of room to afford is to over design, because in the structures and thermal world, when we over design, it's heavy, right? And when it's too heavy, every ounce counts, right? So it changes the dynamics, it changes kinematics, and it changes the cost. Let's be honest, right? Every pound costs a certain dollar amount to take a ride up, right, to low Earth orbit. So I think one of the coolest aspects of getting it to tie in is that I don't have to do that math now. I don't need to sort of create overly conservative thermal environment. I can say, okay, at this point in the mission, this is the thermal load, analyze it. At this point in the mission, this is the thermal load, analyze it. And I actually have the DME tools and my power output for my electrical engineers. I have this combination of these mission profiles. I have them tell me what the worst case scenario is. That
Hmm.
way I'm not injecting in some overly conservative environment. So to me, that's the coolest thing. Again, from like a designer and analyst perspective.
Hmm. Yeah, that's great points, Jim. I want to answer that one with a real world example of tying in from the smallest level component level is put inside of a system, and then that system's put inside of another system, and then systems. It all builds up, and then analyzing all of that together through the pipeline is what DME helps to do in conjunction with the standard physics solver tools that Jim was talking about. And the real world example I'll give you is a very high profile, very hard engineering problem, which was the James Webb Space Telescope. So the James Webb Space Telescope has some very complicated optics and mechanics to make sure things function properly when they're up in space, and it's super cold, and then they're also trying to use very sensitive optics up there, and those things change, and those conditions are something that DME fed over so that they could design to them. And in the same tools, not only were the optics and the mechanics and the sun blocking things designed, they also designed the trajectory itself. So going out, and James Webb has a non-trivial orbit as well. It's a complicated orbit to get into. And it's a complicated orbit to model. And if you can model that orbit realistically, now you know what all those thermal loads are. Now you can design the most sophisticated telescope in the history of mankind, because you can go from that component level all the way up to, well, now it's on station and it's trying to observe the universe. And you can do all of that with these tools. And that's pretty exciting, because that's a real breakthrough technology.
I mean, if you see the pictures that come off of James Webb, I mean, I don't know what other evidence you need, for those to understand how much sort of optical design and analysis needs to go in, but those images are ridiculous,
Yeah.
and yeah, it's very cool to see.